Hey guys, and welcome back to another video on the channel. In today's video we're going to be going over the introduction to a geometric sequence. In the previous videos we've taken a look at arithmetic sequences. In today's video we're just going to get started on geometric sequences. So the main difference between arithmetic and geometric is pretty much instead of adding or subtracting a constant, we're multiplying or dividing a constant. So for example, for an arithmetic series we had 1, 2, 3, 4. We also had -1, -2, etc. and stuff like that. As you can see, it's increasing or decreasing by a constant amount. So for example, here it's going by +1 and here it's going by -1. A geometric series is basically that. Instead of adding or subtracting, it's multiplying or dividing. Most of the time we think of it as multiplying, and if it's dividing we just think of it as timesing by its reciprocal. So for example, if we have this is a geometric series. We have 2, 4, 8, and we can see it's both getting times by 2. Okay, so for example, the next term in this sequence would be 16, because that's being times by 2. We could also have this following sequence where we have 16, 8, 4, 2. We can see it's getting times by a half. So we like to think of it as like a reciprocal. So rather than saying divide by 2, it's being times by a half. Okay, so that's the main idea of a geometric sequence. Okay, so recall the number of sequences called its term. So the nth term of a sequence is denoted by Tn. So the first term is T of 1 and the 12th term is T of 12, and so on and so forth. A sequence in which its successive term is found by multiplying by the previous term is by a fixed amount is called geometric sequence. So pretty much it's multiplying or dividing by a constant amount. Geometric sequence has a relation given this form here where r is a constant. So in other words, what this is saying is, alright, if you want some term, so for example the second term is your constant you're multiplying by the previous term. So for example, you see how it has t of n and this is t of n minus 1. Well, n is the term after n minus 1, because if I have, like, let's say n is 6, that means this would be 6 and this would be 5. So it's the previous term pretty much. So that's what that pretty much means. So if you see t of n equals r times by t of n minus 1, it means, alright, to work out my next term I need my constant, I multiply by the previous term. Okay, and then they have an example of a geometric sequence here. This one, it's getting times by 3 and so on and so forth. Okay, let's go to the next slide. So the nth term of a geometric sequence is given by this formula here. So like an arithmetic sequence, when we got given this formula here, we've got pretty much the same thing for a geometric. So that was for arithmetic here. This one is for geometric. So you have t of n is going to be your first term times by your constant ratio to the power of n minus 1. Okay, so we can see there's a couple similarities here. Now you can actually update this formula by getting rid of the 1 if you really wanted to, because you can just change it. Okay, as long as you keep this and this their same number, and as long as this term is before this term here. So for example, if this is t of 3, this has to be at least t of 2. Okay, it can't be like t of 4. It has to be a term before t of 3. Okay, otherwise it gets a bit messy. So we can actually replace this to this formula. So we have t of n is equal to t of k times by r to the power of n minus k. So the only thing here we did was change the 1 to a k. So change a couple indexes. Okay, r is the common ratio of the successive terms. It's given like this. So pretty much if you want to work out r, you want to divide one term by the other. So for example, if we had this geometric sequence, so we had 2, 4, 8, 16, what we want to do is, alright, that's my first term and that's my second term. So r is going to be t of 2 divided by t of 1. So that's what that means there. So in other words, we're going to have 4 over 2, which gives us 2. We could have also worked it out by going, alright, that's t of 4. So we could have, alright, t of 4 on t of 2. See what that is. That wouldn't, actually no, that doesn't work, because you got to have the previous term, sorry. Has to be the term right next to it. So it has to be t of 3 then. So t of 3, t of 2. So you're going to have 8 on 4, which gives you 2. Okay, so that's what that pretty much means there. Yeah, and that's about it. Let's rub this out. This is a very similar way to writing this formula here. So A is just T of 1. So if you see that in books, it's literally the exact same formula as this one up here. I don't know why they changed it like that. Just stick with one, honestly. Whether it's this one or this one, whatever you're more comfortable with. But just know if you do see the other one written, know what it means pretty much. Because they're going to switch back and forth for some reason. Okay, let's get into some basic questions about this stuff. Okay, so example 1. Find the 10th term of the sequence here. Okay, so this sequence here, we can see we got to find our common ratio. So we know our first term is 2. And we see it's getting multiplied by 3. Okay, so your R is 3. So now we write the formula because we're looking for the 10th term. Okay, so T of n is equal to T of 1 times by R to the power of n minus 1. So T of n is going to be 2 times by R, R is 3, sorry. 3 to the power of n minus 1. So if I want T of n, I can replace this index here with the 10. So I'll have T of 10 equals 2 times by 3 to the power of 10 minus 1. So you're going to have 2 times by 3 to the power of 9. I'm actually not fully sure what that is, so I'm going to put in my calculator. 2 times 3 to the power of 9. 39366. There's no way anyone would work that out in their head unless they're like a genius. And that's how you would answer the first one, okay? If you have any questions about these example here, try and leave something in the comments and I'll try my best to answer them. But let's go on to the next example. Right, so for a geometric sequence, the first term is 18 and the fourth term is 144. Find the common ratio. Okay, so T of 1 is 18 and T of 4 is 144. Okay, so we have this formula here, but we can actually update it if we want to. So for example, this doesn't need to be a 1, this can actually be any number we really want. So we can actually update it to this formula here. So we have T of n equals T of k times by R to the power of n minus k. Okay, so we're just trying to find R. So what we can do is just substitute this information into here if we want. Now, it just so happens we got given the first term, but we can pretty much do whatever it wants. I think I read the question too fast and thought that was a different term. But you can use this formula if you want. It doesn't make any difference. But let's just use the original one now. So we have T of n equals T of 1 times by R to the power of n minus 1. So here we're going to have T of 4 equals T of 1 times by R to the power of 4 minus 1, which is 3. I now know what this is. This is 144, and I do know what this is. That is 18, so I can plug that in. So I'll have 144 equals 18 times by R cubed. So I can divide both sides by 18. 144 divided by 18 is going to be 8, so 8 equals R cubed. Then you're going to cube root both sides to undo that cube. So you're going to have R is equal to the cube root of 8, which I believe is 2. Yeah, maybe. Yeah, 2. Right. That's our example down. Let's move on to the next one. Okay, so for a geometric sequence, 36, 18, 9, find the nth term, that is 9 on 16. Okay, so we can see this one is decreasing. Okay, so 36 to 18. We've got to think, okay, how much is that decreasing by? So if you want to find R, you need that term divided by, this term, so 18 divided by 36. Because if I had it the other way, then my R would be a positive whole number, so it would be increasing constantly. It needs to be a fraction less than 1 because it's being divided by a certain amount. So 18 divided by 36 is going to give me a half. Okay. Now you probably could have worked that out straight away, but in case you didn't work that out straight away, you just take this term and divide by this term here. So in other words, we could have worked it out if we had 9 divided by 18. That would have also given us a half as well. Okay. So R is a half. Drop this stuff out now. And we're trying to find this term here. So T of n is 9 on 16. Okay, so we have our formula here. T of n equals t of 1 times by r to the power of n minus 1. We also know what t of 1 is. It's 36. So I can substitute this information here, and I can also substitute this information here. And while we're at it, we can actually just substitute this information here. And I'll show you why in a sec. So if I do that, I'll have 9 on 16 gives you 36 times by a half to the power of n minus 1. Okay? So now all we're going to do is solve this for n. So what we're going to do is, alright, divide both sides by 36. So that cancels out. So you're going to have 9 over 16 times by 1 on 36. So that's going to give you 1 on 64 on this side. So 1 on 64. And then you have a half n minus 1. Okay? So I'm just going to rewrite up here. Now you're probably thinking, oh, do we have to do logs? Not necessarily at the moment. We can break this up using index law. So a half n minus 1 is the same as, well, 2 times by a half to the power of n, when you think about it, because 2 is just a half to the power of negative 1. So in other words, I've got, let's rub some stuff out so I have a bit of room for this. So if we remember our index law, if we have a to the n times by a to the m, you can add those indexes together. Okay? So what we have is something in reverse. We've got a half to the power of n minus 1. That is the same as a half to the power of n times by a half to the power of negative 1, which is the same as 2, because if you have a half to the power of negative 1, you have 1 to the power of negative 1 over 2 to the negative 1. So the way you flip those exponents to be positive is you tip in times, so, or not tip in times, you just flip it pretty much and you'll get 2 on 1, which is just 2. Okay, so that's why I made that step there. Let's rub this stuff out so I have a bit of room now. So now I have 1 on 64 is equal to 2 times by a half to the power of n. Okay, what I'm going to do now is divide both sides by 2. So I'm going to have 64 times by 2, which is 128. So I have 128 gives me 1 on 2 all to the power of n. Now I'm going to distribute this n really quickly. So I'll have 1 on 128 gives me 1 to the power of n over 2 to the power of n. 1 to the power of n is just 1, no matter what value of n you put in there. You could put in a million, a trillion, doesn't matter, it will always be 1. So we can just simplify that top bit. So I'm going to rub this stuff out. So I'll have 1 on 128 equals 1 on 2n. So if these two are both equal, that means, let's use a different color. Let's use pink. This is equivalent to this. So 128 is equal to 2 to the power of n. So I've got to pretty much think, okay, 28. How can that be represented as a power of 2? Well, starters, we got to think, okay, 28, that is divisible by 2, but how many times can that really fit in? So, for example, I've got to just try and break up a couple numbers. So I know 2 to the power of 3 is 8. I've got to think, okay, is 128 divisible by 8? Yes, it is. You've got 128 is the same as 8 times by 16, I think. Now, 8 can be represented as 2 to the power of 3. 16 is the same as 2 times by 8, isn't it? So in other words, I've got 2 to the power of 3 times by 2 times by 2 to the power of 3. Add up all those indices, I get 2 to the power of 7. So 128 is the same as 2 to the power of 7. So 2 to the n. So that means n is 7. So I did all that without logs. A lot of algebra and a lot of index laws, but no logs. So you don't need logs to answer this question here. Okay. Alright. If you have any questions about this particular one, leave something in the comments and I'll try my best to answer them. But let's head on to the next example. Okay, so the third term of a geometric sequence is 10, and the sixth term is 80. Find the common ratio in the first term. Okay, so in this scenario here, we can't really use this formula. The reason why is because we haven't been given the first term, but we can update this to our previous formula that I've mentioned earlier. So T of k times by r to the n minus k. So all I did there was replace the 1 with a k. Okay? No pun intended there. Okay, so what do we have given? The third term is 10, and the sixth term is 80. Now, I can use this formula because they're always saying geometric sequence. Now, the reason why I haven't actually been checking the questions is because, well, I know this is from the geometric series chapter, but in books and questions, you've got to check, alright, geometric, arithmetic, all these stuff here pretty much, okay? Righto, so, let's just get straight to working. So, you've got to place your bigger term here, so this will be T of 6, and this can be T of 3, okay? Times by R, and then replace this with what you had here, so 6, and then replace this with 3. We know what T of 6 is, it's 80, and we know what T of 3 is, it's 10, times by R to the power of 3. So therefore you're going to have 8 equals R cubed, therefore R is going to be the cube root of 8, which is 2. And that's it for this video. In the next video I'll cover this last example here, which is a bit more complex, and then a couple of practice questions pretty much. But yeah, if you enjoyed this video, give it a thumbs up, like and subscribe. I'll be doing tons of videos on math methods pretty much. But yeah, I hope you enjoyed.